Alright, Technetium-99. Technetium-99 is a really useful isotope of technetium in medicine because it can be easily bonded to different organic molecules, and then we can use it as a marker that can read blood flow either around the whole body or in particular organs like the heart or other vital organs, and doctors can use it to find blockages or to check that everything's working fine. What's great about it, besides the fact that we can easily bond it, is the fact that it's got a half-life of only 6 hours. What that means is that we can put enough technetium-99 into someone that the radiation is visible outside the body, but then it dies off so quickly that they're not left with a total dose that's very high. So the total exposure dose is kept low, but it gives off enough radiation to be detected outside the body. Now, a half-life of 6 hours, half-life. Now, the problem with a half-life of 6 hours means that after 6 hours you got half, after 12 hours you got a quarter, after 18 hours you've now got an eighth, and after 4 days you've got less than 0.1%. So this short half-life means that if you do have a sample of technetium-99 in a week, you're not going to have a sample of technetium-99, and that means that you need to produce it on site. I suppose the other reason you could say that it's great is because it's easy to produce. There's probably many different isotopes that would be excellent to use in this kind of a role, if only they could produce them easily. Technetium-99 they can produce on site in a hospital. What they do is the hospital gets a source of molybdenum-99. Now you remember molybdenum has that atomic number of 42. Now Seaborg converted not molybdenum-99, converted molybdenum-95 to technetium by smashing in that deuterium molecule. But this isn't what's going to go on here. What happens to molybdenum-99 is it undergoes beta decay. So beta decay, one of these neutrons is converted to a proton. So the atomic weight is unchanged, but the atomic number goes up by 1. So we get technetium-99 plus an electron. Now the great thing about molybdenum-99 is that nuclear reactors, when uranium breaks down, it's one of the there's quite a few products, but it is one of the products that we can separate out of a nuclear reactor. We can then put it in what's known as a cow, which is it's a special apparatus. Basically, you can dissolve all this molybdenum. Or you can kind of combine it with a sulfate kind of mix in a solid, if I recall correctly, and then there's a liquid. Now, the molybdenum that stays as molybdenum stays in this solid, but when it changes to technetium, now it's a new element, it's got new chemical properties. What happens is that I believe it's a sulfate that it's kind of bonded to. It's not as tightly bonded to it. It then dissolves out into the liquid, and the liquid becomes rich in technetium-99, and then you can add that liquid to the various organic molecules and then use it as a marker for medicine. And this whole device can sit in the hospital, so it's delivered full of molybdenum, but then over the next week or so it produces this technetium-99. And the whole thing is of course shielded so that excess radiation doesn't get anybody in the hospital. But this is all able to be done on quite a small scale. These can be moved around by an individual, stored safely in the hospital, and you get the particular isotope that you need for medical purposes straight away. So Technetium-99. The reason I'm going on about it for so long is that we'll need to know about it. By the way, molybdenum-99, its half-life is more like, I believe it's 66 hours, not 6. So it's got a much longer half-life, which means this thing can sit here for a week or so before it's lost most of its ability to generate technetium. So the hospital only needs to take delivery of one of these every week. Doesn't have to take a delivery of them maybe once a day, which is what would have to be the case if they were just getting technetium delivered. Great, so that's nuclear chemistry for the HSC.